Chapter 3, Section 3.2 Exponential Growth and Decay, Constant Percentage Rates. An exponential function is a function that changes at a constant percentage rate. For example, if a population triples each hour, does this represent constant percentage growth? If so, what is the percentage increase each hour? Is the population size an exponential function of time? Solution. The population changes each hour. The population next hour is equal to 3 times the current population. So if we start with 100 individuals, initial population is 100. And population after 1 hour is 3 times the initial population, which is 300. Population after 2 hours is 3 times 300, which is the population after 1 hour. And that's equal to 900. So what kind of growth do we see here? Growth over the first hour is 300 minus 100, which is equal to 200. And that's 200% increase over 100. Growth over second hour is 900 minus 300 equals to 600, and that's 200% increase over 300. The population is growing at a constant percentage rate of 200% each hour. Thus, the population is an exponential function of time. The formula for an exponential function y of t is y equals to initial value times base to the power of t. In our previous example, initial value was 100 and the base was 3. The previous example function is y equals to 100 times 3 to the power of t. An exponential function y of t is characterized by the following property. When t increases by 1, to find a new value of y, we multiply the current value by the base. The y value for t plus 1 is base time y value for t. Example. The value of a certain investment grows according to the rule. Next year's balance is 1 700 times current balance. Find the percentage increase each year and explain why the balance is an exponential function of time. Assume that the original investment is 800. Find an exponential formula that gives the balance in terms of time. What is the balance after 10 years? Next year's balance is 1 700 times this year's balance. Next year's balance is 107% of this year's balance. That's 7% increase per year. Because the balance grows by the same percentage each year, it is an exponential function of time. Here, B is the balance in dollars after t years. B is equal to initial value times base to the power of t, which is the formula we saw on the previous page. The initial value of investment is 800 and the base is 1 700. This gives the formula B equals to 800 times 1 700 to the power of t. The balance after 10 years is 800 times 1 700 to the power of 10. The t value, the time, is equal to 10. Example. Suppose that a certain job opportunity offers a starting salary of $50,000 and includes 5% salary raise each year. In evaluating this opportunity, you may wish to know what your salary will be after 15 years. Solution. A 5% annual rise means that the next year's salary is 105% of the current salary. Next year's salary is 1/500 times current salary. We know that our salary is given by the exponential formula with initial value of 50,000 and base is 1 500. We can plug these values into the formula. The salary is 50,000 times 1 5 times to the power of t. And then to find what the salary is after 15 years, we're going to plug in 15 for t and evaluate. The key observation in this example is that the salary is an exponential function and the base corresponding to 5% is 1 and 500. A common error would be to assume that 5% raise for 15 years is the same as 15 times 5%, which is 75% raise. The actual raise is actually much more. Exponential growth. A quantity grows exponentially when it increases by a constant percentage over a given period. If r is a percentage growth per period, then the base of the exponential function is 1 plus r. For the exponential growth, the base is always greater than 1. The amount is equal to initial value times 1 plus r to the power of t. Here t is the number of periods. Typically, exponential growth starts slowly and then increases rapidly. For example, US healthcare expenditures in 2010 reached $2.47 trillion. It is difficult to predict future healthcare costs, especially with the advent of the Affordable Care Act. One prediction is that in the near term, they will grow by 6 and 0.5% each year. Assuming that this growth rate continues, find the formula that gives healthcare expenditures as a function of time. If this trend continues, what will healthcare expenditures will be in 2030? Solution. Let age be the expenditures t years after 2010. We're assuming that we have a constant growth rate of 6.5%. This is a constant growth rate, therefore we have an exponential function. Here the growth rate is 6.5%, and this growth is going to continue. So each year the expenditure will increase by 6.5%. And that's the key to using the exponential formula here. That's why we're using it. Then we'll plug in the values that we have. The initial value is going to be $2.47 trillion. R in decimal form is 65,000. We'll plug this into the formula, and we can use it to predict the healthcare expenditures in 2030. Use t for t equal to 20 for our time. Expenditures in 2030 are 2.47 times 1 plus 65,000 to the power of $20 trillion. This is going to be our graph. This is a graph of expenditures, healthcare expenditures. This is a graph of an exponential function. Notice that this function is increasing. It's increasing because it's a growth function. Exponential decay. A quantity decays exponentially when it decreases by a constant percentage over a given period. If r is a percentage decay per period, then the base of the exponential function is 1 minus r. For exponential decay, the base is always less than 1. Amount is initial value times 1 minus r to the power of t. Here t is the number of periods. Typically, exponential decay is rapid at first, but eventually slows. Example. After antibiotics are administered, the concentration in the bloodstream declines over time. Suppose that 70 milligrams of amoxicillin are injected and that the amount of a drug in the bloodstream declines by 49% each hour. Find an exponential formula that gives the amount of amoxicillin in the bloodstream as a function of time since the injection. Another injection will be required when the level declines to 10 milligrams. Will another injection be required before 5 hours? Solution. Let A be the amount of amoxicillin in the bloodstream after t hours. The base of the exponential function is 1 minus r, which is equal to 5100. The initial value is 70 milligrams. We just plug this into the formula. We'll get 70 times 5100 to the power of t. To find the amount of amoxicillin after 5 hours, A is equal to 70 times 5100 to the power of 5, which is 2 and 4 tenths milligrams. The result is about 2 and 4 tenths milligrams, which is less than a minimum of 10 milligrams. Thus, another injection will be needed before 5 hours. The graph shows that the level declines to 10 milligrams in about 3 hours. This is a graph of exponential function, and this function is exponential decay. It's a decreasing function. It's a decaying function. The half-life of a radioactive substance is the time it takes for half of the substance to decay. After h half-lives, the amount of radioactive substance remaining is given by the exponential formula. Amount remaining is initial amount times 1/2 to the power of t. We can find the amount remaining after t years by first expressing t in terms of half-lives and then using the formula above. For example, the carbon-14 in an organism decays with a half-life of 5,770 years. That is, it takes 5,770 years for half of the carbon-14 to disappear from the living organism. Suppose a tree contains C0 grams of carbon-14 when it was cut down. What percentage of the original amount of carbon-14 would we find if it was cut down 30,000 years ago? Solution. The amount C remaining after h half-life is equal to C0 times 1/2 to the power of h. 30,000 years. How many half-lives is that? We can find it by dividing 30,000 years by 5,770. That results in 5 and 2 tenths half-lives. So the amount after 30,000 years is the initial amount of carbon-14 times 1/2 to the power of the number of half-lives, which is 5 and 2 tenths. That results in 27,000 C0 grams. That means that about 2 and 7/10% of the original amount of carbon-14 remains after 30,000 years.